right, good morning, everyone. I have 8:30 on my clock, so we're going to go ahead and get started. This is Liz John and Marielle with Spear, and thank you for joining us this morning for our Speakers Bureau webinar. As many of you know who've been joining us for a while, we're a nonprofit and we work to advance energy efficiency in Texas and Oklahoma. And one way we do that is through our Energy Codes program by promoting compliance with state energy codes. And this is done through training, outreach, and peer support. As a part of that effort, we bring you these Energy Code webinars every other Wednesday morning. And today we have Corey Hines with Daikin, and he will be presenting on designing the VRF projects to meet ASHRAE 15. Just a few quick notes before I turn it over to Corey. All attendees are muted, and if you have a question, please feel free to type it into the Q&A panel. We'll answer it at the end of the webinar. If by some chance we don't have time to get to it, I will send those over to Corey and he will be able to answer those directly. These webinars are RCC certified, so if you're watching live, we will issue those within the week. After the webinar, we'll send you out an evaluation form, and in order to be ready for the ICC certifications, you'll need to complete those surveys. With that said, I will turn it over to Corey and have him introduce himself, and we will get started.
Great. Thank you so much, Liz. My name is Corey Hines. I'm with Daikin. I've been in the air conditioning industry since 2001. I've had a chance to work with a lot of different types of products over time in different projects across the United States and Canada. Back in 2001, started working with the VRF product and have really enjoyed VRF, and it's been a lot of fun to watch VRF extend and expand across North America. So today we'll be talking about designing VRF projects to meet ASHRAE 15. So really appreciate your time and attention to the subject, and look forward to hearing your questions at the end of the presentation. So today we'll be talking about, I'm going to give a brief overview of Daikin. We'll talk a little bit about the history of VRF. Then after that, I'll talk about codes and just provide an overview on codes, the overarching codes for VRF projects. Then I'll get into ASHRAE Standards 15 and 34, and I'll talk about how those two codes are intermingled. And after that, we'll talk about refrigerant concentration limits. What does that mean? Where'd that come from? And then finally, we'll wrap up with examples and methodologies for resolving ASHRAE 15 scenarios. So look forward to talking with you about these topics. And but first, I want to talk a little bit about Daikin. We are the #1, the largest in terms of volume manufacturer of air conditioning products in the world. We are fully focused on air conditioning, not tied to other things like such as aerospace and other types of industries. Our company is focused on VRF, actually having innovated it 37 years ago, and we've been making innovations in HVAC for over 95 years this year. We have also, with regard to refrigerant, 10% of our company's focused on refrigerant, and in that realm, we recently released and made public the patents for R32, which in 2023 will be one of the new refrigerants that you'll see out in the marketplace, used in different types of mechanical equipment. And so the goal of sharing that patent was to allow that patent and that refrigerant to be used by other manufacturers around the world. As a company, we have focused over the years on heat pump technology. We've also focused on inverter technology as well. And with inverter technology, you may be aware that we're able to meet the load in any space at any given time. So instead of having a compressor fully on or fully off, our compressors modulate to keep the building comfortable and and it also makes our units a lot more energy efficient. We also focus on refrigerant control and the efficient transport of heat within the space. And that's part of how VRF itself works as a technology. We're a global company, and we're number one around the world throughout all the continents. And we're not number one yet in the US, but we're growing very rapidly. Some of you might be familiar with our Daikin, Texas Technology Park. It's located down near Houston, Texas, and Waller, Texas, about 39 miles northwest of downtown Houston. And in Waller, we have a 4.2 million square foot facility. One of the things that's really important to our company is to have a global base and be based within each country in which we do business on a daily basis. So in North America, our contribution is bringing in, at the moment, we have more than actually 5,000 employees down in Waller. And by the end of the year, we expect that number to grow to 8,500 with the startup of our building rooftop units at the facility there. In addition to building rooftop units, we actually build all of our unitary products, light commercial products, 1.5 to 25 tons. So that's residential split systems, PTAC units, and of course we build our VRF. We use the term, you'll even use the terms VRF and VRV interchangeably today. VRV is variable refrigerant volume, whereas the trade name is VRF, variable refrigerant flow. We actually build our VRV outdoor units down in Waller, Texas as well. A little bit about the history of VRF. VRF actually started in Asia. It addressed a lot of problems with regard to space, limited space. If you've ever been to Japan, you know, a lot of the rooms, a lot of the buildings and things are built very tightly in a lot of confined spaces. VRF was invented in 1982 by Daikin and built up very quickly in its growth across Asia, then going to Europe, Africa, and to South America and Latin America. And is growing very rapidly here in the US. And since that time, since 1982, and you know, there have been over 1 million installations of VRF, VRV equipment around the world. There's actually been over 60,000 systems installed in the US and Canada. And that's just actually since the early 2000s when the technology first came to the United States. We've had a large commercial adoption of VRF, and our adoption rate in the US is about 5% of the 15% or so of all the VRF or all the HVAC projects that utilize VRF. So VRF's adoption has taken hold very quickly. So, you know, some of the things that have drawn people to VRF are comfort, modular design, ultra high efficiencies, and exceptional comfort control. Comfort control probably being one of the leading things that draws building owners to VRF. And so just a little bit of history about VRF. We developed the first VRF system, trademarking it VRV back in 1982. We actually took the technology during the late 80s, shared it just like we're doing with refrigerant, and allowed other manufacturers to enter the space. And of course, that actually helped the product type grow with the first VRV inverter compressor being launched and released by us in 1990. Since that time, there's been a lot of focus and concentration on VRF products providing cooling and heating at low temperatures. And so in early 2003, we released a product that allows heating down to -4. And if you look across the screen to the far right, you'll see that in 2018, we launched another groundbreaking product that allows us to do 60% of the rated heating capacity at blistering -22 degrees Fahrenheit. VRV technology has continued to grow and develop since that time with continuous heating and defrost being implemented. into the product. We also have single phase products that are being utilized not only in light commercial projects, but also in homes as well. And we've also gone into more tall buildings by allowing the use of VRF technology with the use of water-cooled outdoor units. And early this year, we even relaunched a product that integrates VRF technology with a dual fuel capability, where we can have the implementation of a gas furnace on a heat pump VRF system. And another big release has been the use of VRF, VRV in scalable buildings, and or what we call shell and core buildings, which has taken place in a very big way as well. And our new VRV 4X technology allows us to have a lot of capabilities that will allow building owners to install smaller systems or smaller amounts of the systems over time. Codes overview. So the U.S. does not have an official national building code, but instead, each state, as new codes are developed, states have chosen to adopt codes and modify those codes to meet their specific state or local needs. Some states and some cities have even adopted their own codes. For example, here in Texas, back in 2017, many municipalities very quickly adopted code IECC 2015 as it was released and accepted at a state level. Standards are voluntary for the most part across a lot of cities, states, and municipalities, but they do give us a good guideline for how to construct or to renovate a building. It's common for a lot of codes to refer to nationally recognized standards and even global recognized standards. And however, many manufacturers tend to focus on national standards. So basically, the process for codes tends to be that a standard is developed by a governing organization such as ASHRAE. Then it becomes a model code through the International Building Code, and then it's accepted as a state law. Some of the primary building code bodies that we have and interact with on a daily basis in the HVAC industry are the International Code Council, or ICC, the International Association of Plumbing and Mechanical Officials, and the National Fire Protection Association. A lot of codes are written by standard writing organizations that set standards for testing equipment, such as the Underwriters Laboratory, and the AMCA, the Air Movement and Control Association. The American Society of Heating, Refrigeration, and Air Conditioning tends to be a big governing body, ASHRAE, as we're called. And other codes are created by the mechanical entities, such as the American Society of Mechanical Engineers and or the American Society of Civil Engineers. A lot of industry and professional organizations publish these standards, and the primary author for HVAC standards tends to be done by ASHRAE. Codes governing VRF projects. There are a long list of about 20 different popular codes, and here we've listed several of these codes that get used on a regular basis. Today I'll be talking about ASHRAE Standard 15, which is the safety standard for refrigeration systems. And it's hard to talk about ASHRAE 15 without talking about ASHRAE Standard 34, which is the designation and classification of refrigerants. Other codes that are very popular and used quite a bit in our industry are the ASHRAE Standard 55, which is thermal environmental conditions for human occupancy, ASHRAE Standard 62, which is the ventilation acceptable for indoor air quality, and ASHRAE 90.1, which is the industry standard for buildings except for low-rise residential buildings. ASHRAE 90.1 actually governs a lot of the efficiency standards that are used for the acceptance of VRF. And then there's also the standard for the design of high-performance green buildings, which is ASHRAE Standard 189.1. So as I mentioned earlier, ASHRAE is actually the organization that develops and implements a lot of the standards and codes that are used, particularly with VRF projects and other green building projects. So other codes that govern VRF are safety and electrical, efficiency and performance, installation and application, as well as the Federal Trade Commission. So while all these different segments of codes affect VRF projects, they all talk about the safety and electrical, and specifically, I'll be talking about ASHRAE Standard 15 and 34. The ASHRAE Standards 15 and 34 are codes that are adopted by a lot of local cities and counties. ASHRAE Standard 15, as I mentioned earlier, is the safety standard for refrigeration systems. So this standard specifies how buildings can be safely designed, constructed, and equipment installed and operated. And the goal of this code is to establish a safeguard for life, limb, health, and property, and also give us some safety requirements. So this standard will typically be applied to the design, construction, testing, installation, operation, inspection of mechanical systems. And it will also be applied to modifications or replacement of parts and components if they're not identical in function and capacity. And then finally, allows us to have substitutions for refrigerants that have a different designation. So with ASHRAE 15, there are a lot of different occupancy classifications. And if I were to break down these occupancy classifications, a lot of them are related to institutional, which is important for occupant impairment and with regard to preventing or allowing a quick exit in the case of emergencies. Other occupant classifications are for public assembly areas, such as churches, residential, commercial, such as office and retail, and then also for large mercantile. There are also occupancy classifications through ASHRAE 15 for industrial and refrigerated rooms, which may restrict access and provide a requirement for certain alarms and other things, which I'll mention later in our presentation. Finally, there are mixed classifications when we have two or more occupancy types within the same building. And so in that regard, we'll look at the occupancy that has the most stringent requirements, and that will govern and help us determine the size of the equipment, which I'll talk about that a little more in just a moment. There are also 5 different refrigerant system classifications, such as direct system, an indirect, open spray system, which would be an example of that would be a cooling tower. Good example of a direct system would be a split system or a heater. And there are also some double indirect open spray systems as well. A good example of that would be a geothermal type system. There are also classifications for indirect closed systems and indirect vented closed systems. VRF systems are actually classified as what we call a high probability system. If we were to look a little bit further down in the code, Other high probability systems include PTACs, water source heat pumps, packaged rooftops, and DX splits. Generally, high probability systems are going to be those systems that utilize large amounts or small amounts of DX refrigerant. So as I mentioned, ASHRAE 15 defines and classifies the types of spaces in a building, and it calls out the approach needed to calculate the maximum quantity of refrigerant allowed in said space. I've highlighted over here on the left, just a copy of the code, and here you'll see it talks about things such as section 7.3.1, non-connecting spaces, and 7.3.2 talks about ventilated spaces and how the refrigerant systems should be set up and how they should be regulated. Like I said, it's hard to talk about ASHRAE 15 without talking about ASHRAE Standard 34, which gets into the designation and safety classification of refrigerants. So the purpose of ASHRAE Standard 34 is to establish a simple means of referring to common refrigerants instead of using trade names. It also helps us establish a system for assigning reference numbers and safety classification and refrigeration concentration limits. And the scope of this particular code is to provide an unambiguous system for numbering refrigerants, and then help us assign a composition designating prefixes for the refrigerants. It does not endorse or concur the suitability or application of refrigerants. It merely, if I were to really sum it up, talks about the toxicity levels and concentration levels of refrigerants that are allowable. And we use those concentration levels when we go back to ASHRAE 15 to help us figure out how much of a refrigerant is going to be allowed in a particular space. So if I were to take a snapshot of this code, this is what it looks like. It gives us a long list of hundreds of different refrigerants that have been developed. A lot of these refrigerants that we utilize today, such as R407C, which I've highlighted here, and R410A, are actually isotopes, and which means that they're blends of refrigerants. And so as a refrigerant is developed, ASHRAE 34 helps us figure out what safety group, what allowable level in parts per million are allowed for that refrigerant to be in the space. Helps us figure out if that refrigerant is flammable or toxic, and tells us what refrigeration concentration level is allowed. And so to break that down, overall, ASHRAE 34 defines refrigerants as being flammable or toxic. If you look at the X and Y axis here of this chart, and it gives us 3 different class designations so with regard to that flammability capability or component of the refrigerant. So a class 1 refrigerant may not produce a flame. A class 2 refrigerant, by comparison, may have low flammability, or it may burn based on its velocity. And then a class 3 refrigerant, by comparison, would have higher flammability. The safety groups, which overall are called Group A, Group B, with different levels based on their flammability. The safety group A refrigerants tend to be lower toxicity, and then while the group B refrigerants tend to be higher toxicity. R410A is actually classified as an A1 refrigerant, and thus is low in toxicity and does not produce any flame. Now I'll talk a little bit more in depth about refrigeration concentration limits. So the history of refrigeration concentration limits, or RCLs, like I said, RCL is actually called out in ASHRAE 34. Basically, an RCL, or refrigeration concentration limit, is the maximum amount of refrigerant that's allowed per ASHRAE 34. This came about in a document that was produced back in September of 2000 and published. It was written by a gentleman by the name of James M. Calm. He's a PE based in Virginia. The document that he wrote is called DOE/CE/23810-110, which is a document that was released, published by the Air Conditioning and Refrigeration Technology Institute. And the goal of this document was to define for refrigerants things such as lethality, which is the likelihood of toxic fatalities, cardiac sensation, change of heartbeat or arrhythmia, anesthetic effect, which is the dullness of the senses, and then it also defines the central nervous system effect, or how the refrigerant might change mood. And as I show my icon here, they actually did testing. This testing was actually done on mice, and this testing then was compared back to humans, and how it might affect occupants in the space. Some more key terms related to the history of the refrigeration concentration limits are a term which is called no observable effect level, or the NOEL, which basically says there were no effects observed. Lowest observable effect, which is the concentration level where one test subject shows effects. The median effective concentration, which is a level where 50% of the test subjects show effects. Acute toxicity exposure limit, which is the effect of exposure from a single exposure. And then finally, the oxygen deprivation limit, or ODL, which is the point where the normal amount of oxygen decreases by more than 1 to 2%. So, as a statement of fact, our air tends to be around 20.8 to 21% oxygenated. And so when we drop below that level, by more than 1 to 2%, that's the oxygen deprivation limit. So, like I said, toxicity is defined in that document written and published by the Air Conditioning Refrigeration Association. RCL is defined as that allowable concentration of refrigerant in the air that's determined in accordance to ASHRAE 34. So, the goal, like I said, is to induce the risk of acute toxicity, asphyxiation, and flammability hazards in normally occupied or enclosed spaces. And so, as you look at the charts as you look at the different charts for ASHRAE Standard 15, there are for each refrigerant, like I mentioned earlier, the refrigerant has a trade name, it has a classification that would put it into group A or B. It has an occupational exposure limit that's defined in parts per million, and then it also has a refrigeration concentration limit as well. And that refrigeration concentration limit testing is actually done at sea level. So the basic, when we're looking at R410A, which is utilized in most VRF systems, that concentration level at sea level is 26 pounds per 1,000 cubic feet. And this refrigeration concentration level may be limited to or reduced to 50% if we're located in an institutional facility. And so on this chart, I'm giving some examples of the amount of refrigerant that's allowed if we were at sea level. And for example, If we're in an altitude that is, at sea level, we're right at that 25.98 pounds or 26 pounds per 1,000 cubic feet. If our altitude increases to 1,000 meters or 3,300 feet, then our refrigeration concentration level will start to slightly decrease at that altitude and higher. So it'll actually go to 20.8 pounds. And then if we're at an altitude that is greater than 4,290 feet, then we're going to be at 12.83 pounds. So actually, we have lower refrigeration concentration limits when we're located in a locality that is at a high elevation, as I show below here, such as Calgary, Canada. Now I'll talk about how ASHRAE Standard 15 can be applied in practice to VRF systems by showing you a few examples. There are 4 steps. Step 1, we want to determine the volume of smallest occupied space. Step 2, we want to determine the refrigerant quantity potential of the smallest occupied space. Step 3, we want to check that refrigerant quantity potential does not exceed the allowable concentration level per 1,000 cubic feet. And then step 4, we'll check for routing of piping, which has to be non-obstructive in corridors and lobbies versus the RCL requirements. So non-connecting spaces are spaces where a refrigerant system is located in one or more enclosed occupied spaces that do not connect. That happens quite a bit, as we apply, as we look at a building such as an office. We'll have a lot of enclosed occupied spaces. There also are ventilated spaces where a refrigerant system can be located and might be served by an air handler or an air distribution system. And within ventilated spaces, there are 3 other space classifications. There's closures, where we might have 1 or more spaces arranged in parallel that can be closed off from a refrigerant leak source. There also are, within a space, there's a plenum, which is the space above a suspended ceiling. And this space, unless it's being utilized, as the air conditioning return, actually, when we're doing our calculation, cannot be calculated or included in our volume for the space. Supply and return ducts will actually be typically located within the plenum and will not count when we're calculating our refrigeration quantities. So here's our first example, application example. If we have a 6-ton DX system, so we have a 6-ton VRF outdoor unit, and we've actually got 4 different closed off occupied spaces here. We have first 3 spaces have 20,000 BTU indoor units, and then at the very end of this system, we have a 12,000 BTU fan coil unit that is located in our smallest occupied space, which is actually 1,296 cubic feet. So the question is this allowed by ASHRAE Standard 15? So to figure out what that meant, how much charge is going to be in that system, that's going to be our first step here. We'll look at we'll actually go to a special chart that we have that will tell us, number one, what is the factory charge in the outdoor unit. And in this case, that's 13 pounds, looking at the highlighted blue line. And then we'll look at the lengths of all of our piping runs. So in this case, we had 200 feet altogether of 1/4-inch pipe. We had 3/8 inch. We had 100 feet of 3/8 inch pipe, and 133 feet of 1/2 inch refrigerant piping. So adding that all together, looking at all the refrigerant in the piping and the outdoor unit, the sum is 30.8 pounds of refrigerant. Next, we'll look at the required dilution volume. That's going to be in other words, what's the maximum size space that to which that indoor unit could be applied. So in this case, that space is 131.5 square feet times a 9-foot high ceiling. So that means our smallest space is 1183.6 cubic feet. That, because our space itself is larger than an 1183 cubic feet, we're at 1296 cubic feet. In this example I showed you here, this would be acceptable and allowed by ASHRAE Standard 15. And so our maximum refrigerant charge that we could actually put in that space, we can calculate that by utilizing the following equation, which is our max refrigerant charge equal to the maximum refrigeration concentration limit, which I mentioned earlier for R410A refrigerant is 26 pounds per 1,000 cubic feet. And then that multiplied by the volume of the smallest occupied space, which was 1,296 feet, means that we could have applied up to 33.7 pounds of refrigerant. In actuality, we only have 30.8 pounds of refrigerant being exposed to that space. So in this simple example I've shown you here, our system actually can be utilized in that space and does comply. So sometimes we get into buildings and we have some issues. There's some problem-solving issues. Sometimes the room is too small. So there are a couple different ways that we can go about solving this type of scenario. Number one, we can have a reduced concentration level. And number two, we can increase the dilution volume. So I'll show you how we go about doing that. Method one, reduce concentration level by optimizing our layout. In our initial layout at the top of the screen, you'll see we have we have an outdoor unit at the very top of the building. We've got a long run of pipe that's actually going to be 95 feet to our first branch, where actually our smallest occupied space is located. In this case, if we were to look at how much refrigerant is in the outdoor unit and all the affiliated piping in this system, we have a total charge of 45.4 pounds. That could be a problem for that space. So if we want to reduce the concentration level by optimizing our layout, what we would do is we would take another look at our piping. Let's try to shorten that piping. We actually are able to shorten the pipe run by 45 feet. So our distance to our first branch now, instead of being 95 feet, is a total of 70 feet. And so that gave us a 24% reduction in the total amount of refrigerant charge in that particular system. So our total refrigerant charge now is 40.8 pounds. So that's an example of reducing the concentration level by optimizing the layout. Another way that we can reduce our concentration level would be to replace the single VRV system with multiple smaller and completely separate VRV systems. So at the top of the page, I'm showing you our initial layout where we have a total refrigerant charge of 45.4 pounds. And then we have a revised layout below at the bottom of the screen. And in that revised layout, we actually took the system, we split it up into two smaller systems. And this allowed us to even more greatly reduce our total piping, which of course reduces cost, and also reduce, most importantly, our total refrigerant charge. So now our total refrigerant charge per system is going to be 15.4 pounds. Method two, we would increase the dilution volume. So in this case, what we would do, going back to our first example, let's go back and say that our first space was too small. We might use a ducted fan coil to serve multiple spaces. This then would increase our total dilution volume to the total volume of the sum of the volume of the two spaces as opposed to the singular space. Another thing we might do is we might use the void space as a plenum chamber where we're moving air. So if we're moving air, return air through our plenum, that would then allow us to count that plenum space in our dilution volume. And if we did that across the entire building, now all of those rooms become a singular space. Another thing we could do is we could lay out the rooms differently. Let's assume our smallest room was too small, we could actually raise the ceiling height to a height that provides the required room volume. And this would decrease the available space for installing a fan coil. So we would go to a model, that would allow us, a model indoor unit that would allow us to accommodate that decreased space of the false ceiling void. So in this way, we've also, once again, used method 2 of increasing the dilution volume by raising the ceiling in the smallest space. Then finally, another way to increase the dilution volume would be to have a permanent opening between the rooms. So this could be a false void ceiling, or it could be done through air transfer ducts, transfer grills, which is done quite a bit, or it could be done through door undercuts or a partition wall. That also will allow us to, once again, increase our dilution volume by counting all the rooms as one singular space. So application consideration, something to think about then are the refrigerant. One of the things to keep in mind, is when laying out a VRF project is that the refrigerant space crossing an open space of a passageway must be at least 7.25 feet above the floor, unless the piping is located against the ceiling of such space. And this is all based on the local jurisdiction codes. And then also passages can't be obstructed by refrigerant piping. So the refrigerant piping can't be installed in enclosed stairwells or other areas of egress. And then finally, the refrigerant piping installed in concrete floors should be encased in a concealed pipe or duct. And then finally, refrigerant monitoring. Refrigerant monitoring is required for mechanical rooms, and the refrigerant monitor in the mechanical room actually needs to have audio and visual warning signals. It also has to have sensors near the equipment or the floor, and needs to also activate emergency ventilation. So the continuous ventilation is also required in mechanical rooms, and this has to be around 1/2 of a CFM per square foot of the space. And then we'll go into emergency ventilation based on a signal from the said refrigerant monitor. And that volume is going to be based on ASHRAE Standard 15. Here's an example of the alarms used in the rooms. So I had a chance to show you some examples of different ways that ASHRAE 15 can be applied. For more information, I'd like to reference everyone to Daikin City. That's at www.daikincity.com. You can also go to www.daikincomfort.com as well, and you can gain more information and insights into VRF. I also encourage you to sign up at Daikin City and take a look at our mock city that we've laid out. We give examples on Daikin City of hotels, restaurants, offices, convenience stores, banks, retail, and other types of facilities where VRF can be used and is compared to other traditional products. Also within Daikin City, we also have tools that can be used to help you calculate minimum refrigerant charges that are required. Another good resource, as I mentioned, is ASHRAE. ASHRAE is a very is a body that is helping us develop a lot of the rules to keep people safe and develop the safety standards that are used in the HVAC industry. So I also encourage you to go to ASHRAE.com as well. Appreciate your time and attention today to our topic of ASHRAE 15 and also encompassed with it ASHRAE Standard 34. Appreciate hearing any questions or feedback that you have regarding the presentation.
Thank you, Corey. That was great. I don't see any questions at the moment, which means you must have thoroughly explained everything. I will send out your contact information along with your slides, so that way the attendees will have this material as well as your email. So if they have any questions, they can reach out to you directly. I don't see anything come through. Just a reminder for all of those that are on the line right now, we will be following up with a course evaluation. And if you would like that ICC certificate, please fill that out. Our next webinar will be Wednesday, August 14th. And Corey, if you have nothing else to add, I think this concludes it. And thank you for your time this morning, everyone. We really appreciate it.
My pleasure. Thank you. Thank you for.
All right. Have a good one.
We'll do you too.
Thank you all. Bye-bye.
Bye-bye.